How are you doing today? All right. Thank you for joining us here at reInvent 2017, and thank you for joining us for this Aurora session. I'm Debanjan Saha. I'm General Manager for Amazon Aurora and a few other services. I'm also delighted to have here Gurmeet Singh Gathor and Brandon O'Brien from Expedia, and they are going to join me in a short while to share their experience with Aurora. They have been an early customer. They have been adding a lot of workload to Aurora. I'm sure you'll like to hear from them. So before I start, let me do a quick poll. How many of you have heard about Aurora before? A fair number. And how many of you have used Aurora? Okay, all right, not that many. I'm hoping that after this talk, I'll have a lot of new customers. So quickly, what is Amazon Aurora? So this is a fully managed relational database service that's optimized for the cloud. From a user's perspective, Aurora is a database that has speed and availability of high-end commercial databases, but maintaining simplicity and cost-effectiveness of open-source databases. It's drop-in compatible with MySQL and PostgreSQL. So if you have application which is today running on MySQL and PostgreSQL, you can migrate without any change to your application. It's a simple pay-as-you-go pricing model, and as I mentioned, it's delivered as a fully managed service. Now, from a technical perspective, we have reimagined the relational databases for the cloud. And there are many things that we have done differently. I picked here 3 as an example. And the first one is it's a fully scale-out and distributed design. I'm going to talk about what I mean by that. It's also a service-oriented architecture leveraging other AWS services, both to build various different features of Aurora, as well as making those services available for people who are building cloud-native applications using Aurora. And the third is that we have automated a lot of administrative tasks. This is using the RDS management platform. We use the RDS management platform and we have extended that further so that many of the common database management tasks, you don't have to worry about that anymore. That's already taken care of. So let's talk a little bit about what I mean by scale-out distributed architecture. If you look at a database stack, there are multiple layers. You have a SQL processing layer, you have a transaction processing layer, you have a caching layer, and the 2 things that you don't see there because we have changed it in Aurora is that there is a logging layer and there is a storage layer. We have combined the logging and storage layer together to create a log structure distributed storage layer, which is a key innovation in Aurora. And that's what you see, for example, in the green shaded area, as well as the number of boxes below, which are essentially storage nodes. So what we do is that in the storage layer, we take slices of data, 10 gigabyte slices, and then stripe it across hundreds of storage nodes so that you get the aggregate capacity and the throughput of hundreds of storage nodes behind your storage volume. It is also replicated 6 ways across 3 availability zones, which are essentially 3 different data centers, and with 2 copies in each data center. This is purpose-built for databases, so you're not using any standard storage protocol like iSCSI or NFS or anything like that. All we do is that we stream redo logs from the head node, which is where the database processing is happening, to the storage node, where we recreate all the pages. And that reduces the network traffic between the head node and the storage node. And this is good both for performance, because we are wide striping it. This is good for availability because we have 6 copies. This is also good in order to reduce network traffic, which ultimately results in better performance, both throughput and latency. And I'm going to talk about some of the advantages in the features that we are going to talk about. Now, we also leverage the cloud ecosystem. Here are some of the examples. For example, Aurora is tightly integrated with Lambda functions. So you can, for example, trigger Lambda functions from Aurora stored procedures or triggers. So let's say you want to create a function where if you have 3 failed logins in a span of 5 minutes, you want to send an SMS message to the DBA. That integration with Lambda function make it very simple. It's also integrated with S3. For example, you can load your CSV files, your Excel files from S3 into Aurora. You can store your snapshot or your backups into S3, which we do automatically for you. It is integrated with identity and access management service. So you don't have to do it yourself. You can use your IAM roles to do access control of the Aurora databases. We have recently integrated Aurora with CloudWatch. So a lot of Aurora logs, for example, audit logs, slow query logs, and other logs, you can stream them into CloudWatch, and you can monitor it in CloudWatch. Automation of the administrative task is what RDS provides. So as a DBA, you have to do a lot of things. Now, things on the right-hand side is what a typical DBA will do when you are managing an on-prem database, but if you're using Aurora or RDS, you don't have to. For example, monitoring and failover, backup and point-in-time recovery, security and compliance, scaling of your instances or your storage. All these things are taken care of so that the DBAs can focus on, or application developers can focus on things that really matter to the business, like schema design, query construction, query optimization, etc. So are people using it? Yes, I'm happy to report that Aurora is still the fastest growing service in the AWS history. Of the top 100 AWS customers, 3/4 of them use Aurora today. Here are some of the examples. These are, of course, the people who are public references. We have tens of thousands of customers using Aurora today. So why are people who are moving to Aurora, and why are they moving to Aurora? So there are two types of customers who are moving to Aurora. People who are using open source databases today. We had the MySQL version of Aurora out for roughly about 2.5 years, and we recently announced our PostgreSQL version. So people from the open source engines are moving to Aurora because of the higher performance. In case of MySQL, it's up to 5x. In case of Postgres, it's up to 3x. You get much better availability and durability. And in many cases, depending, of course, on your workload, customers save a lot of money, up to 60%. I have a couple of examples of that. And especially when people are coming from MySQL and Postgres, it's actually very easy to migrate because it's fully compatible with MySQL and Postgres. Any application that is running on those two databases can migrate without any application change. Now, we also have a lot of customers migrating from commercial databases. And the reasons they're migrating are slightly different. So first is it's much cheaper, literally about 1/10 of the cost of commercial databases. There is no licenses to manage. It's very well integrated with the cloud ecosystem. So especially for people who want to build applications in the cloud, it's almost a no-brainer that Aurora provides a much better platform as a relational database than some commercial databases. It has comparable performance and availability. And migration, while not as simple as migrating from open source databases, we have built a lot of tools, schema conversion tool, database migration service, and we also have professional services which help customer migrate from commercial databases to Aurora. Now, let me give you a couple of examples of interesting use cases. These are probably not typical because most of the typical database applications are people moving their operational databases into Aurora. So in this particular case, a genealogy company who needed a high-performance data store for their DNA matching application. And they started with a NoSQL database, Cassandra. And that grew in size as their business grew to 100 nodes. And it became not only difficult to manage, but also very expensive. So they recently moved to Aurora. And they have actually moved to a 10-node cluster, 10 nodes of X large, which is not that big, really. And they do millions of reads and millions of writes, and millions of writes per second. And they have observed less than 10 millisecond latency, and their projected cost has gone down significantly because it's actually a lot easier to manage. They are spending a lot of money both in storage as well as managing their Cassandra cluster. This is another interesting example. This is an on-demand video streaming service which was using a Redis cluster to store a lot of their metadata. And what they had to do is that because they needed some persistence in their data, they had to do occasional backup of that metadata. And that, as the business grew, again, became very complicated, error-prone, and also expensive. So they replaced their backup infrastructure, essentially, with the Aurora cluster behind their Redis cluster, and using Aurora as a persistent data store. And they also, in terms of both management and cost, this was a significant improvement from what they had before. Let me give one more example. This is also kind of an interesting example. This is a financial services company where there are a lot of data which are coming from various different trading platforms in form of transaction streams, sometime in spreadsheets, and they put that data in S3. And what they do is that as data comes into S3, they have a Lambda function which triggers and moves that data into Aurora. We have a function called read from S3. And then they do some, essentially what I would call ETL processing. They do transformation of the data, they do different types of projection, joins, et cetera, and then they move that data either to EMR or Redshift for further processing, right? They also do some reporting and analysis on that data. Some quite interesting use cases. Now, let me move to the next section, which is some of the attributes which people like about Aurora. So Aurora is fast. It is 5x faster than MySQL. This is some slide that I show a lot of people. This is essentially running Sysbench, which is a popular MySQL benchmark on an 8XL node, which is 32 vCPUs and 244 gigabyte of memory. And as you can see from the graph, on the right side, Aurora gives about 120K writes, 120,000 writes per second. On the read side, we get about 600,000 reads per second, and that's roughly about 5x of what you see in MySQL 5.7 or 5.6. We have recently released our R4 16XL, which is twice the size of R3 8XL, and in some of the performance deep dive talks, you will see some results from those experiments that we have done. And it's not just about simple read and write. Aurora actually scales very well. It scales well with number of user connections. In this particular case, as you grow the number of connections from 50 to 5,000, it scales much better than MySQL, up to 5x faster with 5,000 connections. It also scales well with the growth in metadata. For example, number of tables. In this particular case, you see the example from growing from 10 tables to 10,000 tables, and the performance was better by up to 11x. Similarly with size of the database, from 1 gigabyte to almost 1 terabyte, both using Sysbench and TPCC-like benchmark, our performance was much better than what you see in stock MySQL. Now the question is, how do we do that? It was essentially a two-track approach. I talked about some of the architectural innovation in Aurora. That was a major part of it. And there was also a lot of engineering optimization, just going through the code path and optimizing the code path in a very painstaking way. So there are two types of things which gives better performance. One is that we actually do less work. We generate a lot fewer I/O, which minimizes network traffic. We cache prior results. We offload database engines. So a lot of things actually help in terms of doing less work. And then we are also more efficient. This is where the engineering optimizations come into play. We process things asynchronously. We reduce the latency path. We use a lot of lock-free data structures, and we batch a lot of operations together, right? Let me give you a couple of examples. So here is an example of Aurora I/O profile. Now, any database generates a lot of I/O. So I have essentially compared, on the left-hand side, I/O profile of MySQL, and this is actually close to any other database, and on the right-hand side, Aurora. And without getting into too much details, what you see here is that even after 6 copies of writes that you need to do, because we have 6 different copies, we actually generate a lot less I/O. And that is because we are not using standard storage protocols. We are using redo streaming. The difference is in a standard storage protocol, every time you have a dirty page, you have to write a 4K byte block. In our case, we are not doing that. We are essentially sending just the delta, which is where if you scribble in a row, you are generating a few tens of bytes of data, right? We, of course, batch that. Now, just getting into some results here, we ran Sysbench on both setups. And on the MySQL side, after running Sysbench for half an hour, we completed 780K transaction and generated about 7.3 million I/Os, which is roughly about 7.4 I/O per transaction. On the Aurora side, In that 30-minute sysbench run, we had 27 million transactions and roughly about 0.95 I/O per transactions. So we had 35x more transactions in half an hour, and each transaction took 7.7x less I/O. That's an example of doing less work, which is one of the reasons why Aurora has much better throughput. Let me give another example from our engineering optimization. One of the critical components in any database is the lock manager, and MySQL has a lock manager. One of the problems with the MySQL lock manager is that there is a big latch or a mutex in front of the lock manager. So when a transaction is trying to acquire a lock in the lock manager, it essentially gets serialized to that mutex, and at one point in time, there is only one transaction which can go inside the lock manager. We completely rewrote the lock manager and made it a latch-free implementation of the lock manager. And as you can see, you have multiple transactions which can work on multiple lock chains if they are update or delete or insert operations. But if they are scan operations, they actually can be multiple scan operations on the same lock chain. It essentially parallelizes the way the lock manager works, and that's one of the reasons we can handle a lot more connections in parallel. That is the reason we can handle a lot more throughput. So we have been doing a lot of other things. I'm, of course, not going to get into all of this. There are a couple of other Aurora presentations where you will see some of these things explained in more detail. On the read performance side, we worked on smart selector, logical read ahead, read views. Two new things which are coming next is hash join and parallel query. And you are going to hear about that in the deep dive talk. On the right side, we have improved NewMyAware scheduler, latch-free lock manager. This has helped tremendously. On the metadata side, we have improved, for example, our online DDL or online schema change, B-tree concurrency, catalog concurrency, index build, etc. Let me give a quick example where this has been very helpful. Online DDL or online schema change, when you want to change the structure of your database and change the schema. Now, that's a pretty complex operation. You are on the fly changing the table structure, which is very fundamental to the database. So in MySQL, the way it happens, it actually does a full table copy in the back end, right? So while things are going on, in the background, it is creating a new table with a new structure and copying old data over. Of course, it takes a lot of time. It's pretty heavy duty. And sometimes it slows down your DML operation tremendously because it is taking lock on that table. We do it in a very different way. For us, it is a metadata operation. So what we do is that we have a table where we keep different versions of the schema. So we are not really changing anything with respect to the table structure by copying data. There are different schemas which are activated at different times, and we actually do a read, modify, write. We actually do a primitive which essentially modify data in flight as we are writing it and figures out which particular schema applies to that and do the transform on the fly to do that, right? And the result of this is actually pretty amazing. If you look at the online DDL performance on a R3 large machine, which is a small machine, if you look at the size of the database, Aurora takes about 0.25 seconds, right? This is because we are not really doing anything on the data side. It's independent of the size of the data. It's a metadata operation. And in MySQL, depending on the size of the table, it might take 1 hour to up to 14 hours. On R3 8x large, which is 8 times larger than, or 16 times larger than R3 large, again, our time is kind of almost not mentionable. And MySQL, the performance is better because now the data transfer is a little faster because it's a larger machine, but it takes considerable amount of time. So let me switch over to availability. Now, performance, of course, matters, but performance only matters if your database is up. And this is one thing where we spent a lot of time. And one of our core innovation architectural side is our storage system. It's a 6-way replicated storage system, and you might be wondering why is it 6 copies that we keep? Why not 2 copies or 3 copies, which is more common? What we do actually is that it's a quorum-based system. When we write to all 6 nodes, but we wait for 4 of those nodes to return, and when they say that they are stable, we consider that write to be stable. And on the read side, it's a 3 out of 6 read quorum. Now, the advantage of doing it that way is that, remember, we have 2 copies in each availability zone or data center. So if you have a complete data center outage, you still have full read and write availability. And if you have a full data center outage plus 1 more failure, a disk failure or a node failure, you still have full read availability, right? And that is actually very, very important, not just from the point of view of availability. It also helps us in riding out some of, for example, network latencies and jitter in the system, because we are waiting for the fastest 4 nodes to return, and the quorum-based systems gives us much better jitter. We have 15 promotable read replicas, meaning that each replica could be a failover target. So if the master fails, then we pick one of the read replicas, and that becomes the new master. And that operation is pretty fast. I'll show you some data from the field. The read replicas also work for handling read traffic. And we recently added something called a reader endpoint, which essentially load balances across multiple read replicas you have. And very recently, I think it was last week, we added auto-scaling feature to the read replicas. So if you have traffic on the read replica side growing, we automatically can add more read replicas. And if that load is going down, we can reduce the number of replicas. So some data from the field. This is from our entire population of databases that we have. In terms of failover time, 30% of the failover happens within 0 to 5 seconds. Another 40% happens in 5 to 10 seconds, and 25% happens in 10 to 20 seconds. Only about 5% of the failover is above 30 seconds. So it's actually very quick turnaround. We do support cross-region read replicas. Managed read replicas, we actually support 1, but you can create more read replicas if you want read replicas in multiple regions. We do support cross-region snapshot copies, so if you don't want to have live replication, you can copy your snapshot every 30 minutes or every hour, depending on the RPOs or recovery point objective that you want to set. Read replicas are quite popular both for DR as well as storing your data close to where your customers are. But availability is more than just hardware failures or software defects. There are, you need to patch your database, for example, right? We created zero downtime patching for that. Sometimes you need to do large-scale database reorganization. That requires you to take your system down, so we created fast cloning for that. Sometimes DBAs actually make unforced user errors. And you'd like to have an undelete operation so that you can go back in time, right? So we created online point-in-time restore or backtrack operation, which is not out yet, should be out in another couple of weeks or so. So let me give a couple of quick examples here. Zero downtime patching. So when you do patching, typically what happens in the database that you shut down your old database process. And when you do that, all the user sessions which are connected to that process essentially gets terminated. Then you restart the database with the new patch process, and you have to reestablish all the user sessions to that new process, right? That is disruptive to applications. So what we have done instead, that we first start the new process with the new patch as a child process of the current MySQL-D, right? And then we transfer the user sessions and the socket state and the network state, everything, to the new MySQL-D process. And after that, we shut down the old one. As a result, the user actually doesn't see the database sessions going down. It seems like a delay or a bump on the wire, right? A lot less disruptive. It works 95% of the cases. There are some cases where we don't handle it very well. For example, when you have bin log on or where you have SSL connections, et cetera, but we are working on those. Database Backtrack, as I mentioned, this is a feature which is coming soon. What it does is that you can move your database back in time as it's on a time machine. So let's say you, by mistake, drop a table, deleted a row, and you want to get it back. You can put it on a slider, go back in time, get your database back, realize that it's too far back in the past. You can move forward, so you can do back and forth and make sure that you get to the point which is most optimal for you. Moving to the next section, security and monitoring. So we, of course, spend a lot of time in security and monitoring. So we support encryption at rest using your own keys. This is integrated with IMS. We support encryption in transit. This includes cross-region replication, which is all encrypted using SSL. We also use the same technique for cross-region snapshot copy. We support advanced auditing and logging without any performance impact. The emphasis here is really without any performance impact, because doing logging is not difficult. What is difficult is doing it without any performance impact. And we recently released what we call database activity monitoring, where you can monitor what's going on in your database using various different tools. So Aurora Auditing. If you look at MySQL Auditing, what it does is that every operation that is happening, a query, a DDL, a DML, catalog query, catalog entry, a connect operation, all of this operation is converted into a string. Then it goes to a sequencer. Then we write it to a file. And when you do that, you get a huge performance hit, which is something we wanted to avoid. It's particularly important to us because our performance is much higher, meaning that we generate a lot more events that we need to log, right? So if we are impacted by the same thing that happens in MySQL, that will be the long pole on our performance path. So we do it in a different way. Again, we use a lot of lock-free data structures. And all of these operations are parallel, put it in a lock-free data structure, and then we write to multiple files so that we can speed operations up. And the results are quite indicative of what we get. We can actually sustain up to 500K events per second without any impact, right? So that's actually, and if you look at the performance difference between MySQL and Aurora, it's pretty clear. With Audit Op, we are 6.4x times better. With Audit On, we are actually 15.9x times better. This is a new feature that we recently added, database activity monitoring. The audit logs that we generate, we stream that audit logs to Amazon CloudWatch. And once it is in CloudWatch, you can search it for specific events in the log file. You can set various different metrics on it. You can do different visualization using Kibana or your favorite tool. You can set alarms and get notified on specific actions that you want to be notified on. And you can then move that data to S3, and once it is in S3, you can do various different kinds of log analytics using Amazon Athena and can visualize that using Amazon QuickSight. This is essentially a way of doing better service telemetry using Athena and QuickSight. At this point, we pretty much have all the industry certification, SOC, ISO, PCI DSS, which is very important for the financial industry, HIPAA, and most recently, FedRAMP. The new feature which is coming soon, this is actually available on Aurora PostgreSQL. It's going to come to Aurora MySQL sometime very soon, what we call Performance Insight. Right? So what it does is that we have a feature called Enhanced Monitoring. And Enhanced Monitoring gets a lot of information on system-level metrics. And Performance Insight will give you a lot of information about database queries. For example, you can figure out what are the top queries which are taking the most of the time. You can actually drill down into each one of the queries and see where it is spending time. Is it waiting on a lock? Is it waiting on storage? Is it starved for CPU, etc.? It's easy to use. One of the things that people really like about Aurora is the storage management. people actually are very worried about storage management, so worried that they often over-provision it. When I look at our complete RDS fleet, I have seen people over-provisioning storage by 30 to 300%. You don't really need to do that in Aurora. You start with a 10 gig storage segment, and as you add more data, we automatically add more storage up to 64 terabyte. We also do continuous backup and point-in-time recovery. You can take snapshot, as many snapshots you want, does not have any performance impact. And we, of course, on the back end of it, do automatic hit management, restriping, et cetera, so that performance is well balanced. Database cloning, this is a new feature that just came out. So the idea here is that you can clone your database very quickly. Let's say you have a production database, you want to test your test workload on that. You can create a fast clone, which takes a couple of minutes, run your application or test workload on the cloned application, and once you are done, you can delete it, right? It's not only fast, it's also cheap, because it's a copy on write clone. It's not doing deep copy, so you only pay for change data. If anything is different between the clone and the parent volume, that's the only incremental data that you pay for. This is, as you can imagine, very popular with the test workload. People create clones, put it in a different account, run test workload on that, and after that, they delete that. I mentioned this before. We are very interested in leveraging our ecosystem. There are two types of ecosystem that we are integrated with. One is AWS ecosystem, like Lambda, S3, IAM, et cetera. But since we are fully MySQL compatible, we also can leverage the full MySQL ecosystem. So pretty much every ISV which runs on MySQL, and now PostgreSQL, they run unchanged on Aurora. So here are some examples of different ISVs which are supported on Aurora. Now, the advantage of being fully compatible with MySQL or PostgreSQL, that you can create hybrid operation. This is an example where provider of an online marketplace, they are actually moving from on-prem MySQL into Aurora, but they are doing it in multiple steps. The first step is that they have created an Aurora replica in AWS, and they have set up bin log replication from their on-prem database into the Aurora database. And they are actually starting to do some analytical operations on Aurora. The next step of that, they want to cut over their read traffic to Aurora. And the final step is cutting over the write traffic to Aurora. So MySQL compatibility and replication support between the two really helps in doing that. Next, migration. It depends on where you are migrating from. If you are migrating from MySQL and you are migrating from RDS, it's really simple, couple of clicks on the console. If you are migrating from MySQL, Percona, or MariaDB, and you are on EC2 or on-prem, you have to take a snapshot, put it in S3, and we can ingest that snapshot into Aurora. If you are migrating from Oracle or SQL Server or some other database, then the best option is to use database migration service and schema conversion tool. Postgres is kind of similar. Yes. So, hope I made the sell, but ultimately it boils down to the bottom line, and Aurora saves you money. It's no surprise that we are cheaper than commercial databases. If we are not, that will be news. But what is surprising, the Aurora can actually be cheaper than MySQL or PostgreSQL. And the reason for that is that, the way we operate our infrastructure. This is an example of a MySQL cluster, a multi-AZ RDS cluster, where you have a primary and a standby, which does not take any traffic, and then you have two read replicas. And each of these instances have storage attached to it. And the cost of this configuration is $13.62 an hour. When you go to Aurora, your configuration looks like this. First, you don't need the idle standby because your read replica is really a target for your failovers, right? So you get rid of one of the instances. You don't really need separate storage volumes because you have a shared storage volume, and your entire cluster runs on that shared storage volume. Also, there is no provision IOPS to pay for. You pay for I/O that you use. And because of some of the optimizations I talked about in terms of using redo locks rather than standard storage protocol, there is overall reduction in amount of I/O. So the cost of this in this particular example is $9.29 an hour, which is about 32% cheaper. Now, in many situations, depending on your workload, because of the higher performance, you'll be able to use a smaller instance. And if you can go down, for example, from 8XL to 4XL, then your cost can be further reduced, and in this particular example, by 50%. Now, you don't have to take my word for it. There are multiple customers who have publicly talked about cost savings that they have seen from Aurora. Save Software, for example, saved 40% in their consolidation effort. Double Down Interactive saved 67%. These are public statements from them. Autodesk, who recently moved to Aurora, they saw their database connection that they can support going up by up to 7x. Their response time went down by 2x. Their CPU utilization went down by 10x. And they also saved money because they're using smaller instances. Now, let me pause here. Gurmeet and Brandon, if you guys want to take it and share your experience with Aurora. Thank you. Thank you.
Can you hear us okay?
Hello, everyone. My name is Gurmeet Kaur. I work for Expedia, primarily with the databases, migration to AWS, and also adoption of the native databases in AWS.
My name is Brandon O'Brien. I work on all kinds of high-scale, high-performance streaming data systems at Expedia.
Okay, so today we are going to share with you our experiences with Aurora Database. Even though we have quite a few installations of Aurora Database, but there's a particular very interesting use case which we want to share with you. And hopefully you will be able to relate to your applications and take with you the lessons which we have learned. So the use case is to provide some experience to the Expedia travelers on shopping experience with some contextual pricing. For example, strike-through price. I'm sure most of you, when you go to grocery shopping, you see the prices, which are little strike-through price, and that tells you that you are getting a good deal. So the use case is to provide a similar experience to the Expedia shoppers. So there's a strike-through price. You may have noticed that. The difference is that the strike-through is calculated on a constantly changing prices underneath. So we have to ingest the data and process the data and feed it back to our live system. So that's quite a challenge. At the same time, we have to build a system that will compute all these lodging prices in real time, and also build exposing all this data, build a serving layer to provide it back to the customers. So I will hand it over to Brandon to explain to you how the architecture is designed.
All right. So as you heard, we were trying to provide real-time aggregates that were computed from individual price components, and those are constantly changing. So we needed a real-time streaming system that could handle modifying all those prices as they came in. So let me show you what we built. Conceptually, the data flow is very simple. We have a large volume data stream in Kafka with all the lodging prices. We use Apache Storm for streaming distributed processing. It's pulling the data from Kafka, and it's saving it into the data store that we started with, which was Cassandra. And we chose Cassandra to begin with because we knew we needed something with high performance, high scale, and that would work for what we thought we needed. And then on the serving side, we used Node.js to pull the data from Cassandra and serve it to the clients. Now, we wired this all up, we turned it live, and it worked. And it gave us the performance and the scale that we were looking for, and we thought we were done. But then we ran into all these other problems, and we realized the operational overhead that we were running into was a little bit higher than what we were expecting. We had one guy, he was spending about half of his time just keeping the whole thing running, and the biggest piece of that was Cassandra. We realized we couldn't do ad hoc queries. We need to actually write a Spark MapReduce program and deploy that to actually just query our own query our own data. And then in terms of flexibility, so if we wanted to make any schema changes, that was a little bit more painful than we thought. And because this is the way the universe works, we only realized how painful this was becoming after our clients had taken a production dependency on us. And so now we had to support it. So we immediately started looking for another solution that would give us that performance and scale with lower operational cost. And we had heard about Aurora, and we tried it out. So we wired it up, we started testing traffic, we looked at the performance, we looked at what it took to run it in production, and immediately we saw that this was going to work much, much better for our use case. Now, ad hoc queries were much simpler, changes to the schema, as Gurmit will explain later, were much easier, and this has been working for us. So what we're doing with Aurora today, we're storing 1 billion rows, we have 4,000 writes per second, and we have 25,000 reads per second. And across those 25,000 reads, in aggregate, it's returning about 500,000 rows per second. The infrastructure that we're doing this with is, on the Aurora side, we have 6 read replicas. So the 500,000 rows are distributed across the 6 read replicas. On the Storm side, for doing the processing to get the data into Aurora, we have 12 nodes. So more detail on what the infrastructure and what the architecture looks like. So we have the system deployed in 2 separate regions. And let's start over on the right, US East. In the upper left-hand corner there, we have a lodging system, and that's publishing data into Kafka. We have Storm picking that data up from Kafka, and we keep Redis to the side, and we're just looking for duplicate keys so that when we're writing that data into Aurora, we can avoid writing some duplicate keys, and that lets us reduce total write load on the system. And an interesting thing here, we actually have 2 separate independent Aurora instances. And Storm is writing to both, the local Aurora instance and a remote one. And one note, to do that cross-region write, that actually took 10 times the number of threads. And Gurmit will explain why we needed 2 separate Aurora instances. On the read side, we have Node.js. And one interesting thing in this case is, and Gurmit will also explain why this is necessary, the client sends us a very large request. Say for example, it's all hotels in Paris, thousands of hotels. Node.js chunks that into much smaller requests and then does round-robin distribution of those queries across all the read replicas. And for our use case, that was actually key for achieving uniform resource utilization across the read replicas. And again, we have a standard Redis cache just for recently accessed data. And so now I'll hand it over back to Gurmit to explain in more detail what we did with Aurora to make this all work.
Okay, thank you, Brandon. So let me share you what were the requirements which we had to fulfill and what kind of solutions we adopted along the way. So this is a journey. And journey has a lot of bumps on the road and a lot of requirements to start with. So one of the key requirements we had is we need to serve 99% of our traffic with the less than 100 millisecond. That was a very tough requirement, especially with the high volume and the underlying data changes on the way. So the way we did it is the Node.js is splitting the incoming traffic and the incoming request from our clients and then into smaller batches. And then each batch is sent over to individual read replica. So each read replica is processing it, sending it back to the application, and then the application is doing the further processing. So that way, we were able to spread the load across different read replicas. The second key requirement is how do we utilize all these resources in a balanced way? Initially, we tried Aurora's inbuilt load balance, but that somehow didn't work because it was balancing on the connections. So across the read replicas, a few of our replicas were getting all the load, and the remaining one were kind of getting underutilized. So then we also have to take some kind of a custom solution, and what we did is we take the application connection pool onto the load balance, and we spread it across the different read replicas. And that was based on the queries which we are sending. Again, the high volume data ingestion, about 4,000 writes per second. Again, rather than taking every single individual insert state coming in, so we batch it, hold it, and then we send it as a small batches, like a micro batch, that the Storm is taking care of that. I want to talk a little bit more about the multi-region presence and how we solve. As Brendan mentioned it, we are sending to 2 different regions from the application. Okay. Aurora has inbuilt feature of cross-region replication, but there was one limitation. We can have only one managed cross-region replica. That wasn't working for us. So then by sending the traffic from the application to multiple regions, what it did, we are heading only with one-time cross-region cost. And on the other region, now we are able to create, again, a set of different read replicas, because now we got 2 masters. So it served the purpose of having local traffic served by a local region, as well as if one region goes down, it serves as the DR as well. Okay. Debanjan mentioned about the online DDL, and I just can't tell you like how beneficial this feature is. And those of you working on the database migration or database changes, you know the pain when you have to make a schema change, right? So the usual way is you create a new table with a new schema, you transfer the data to that, and that requires a lot of processing or maybe customization, creating smaller batches, managing the process, quite a painful process. So we tried fast DDL, that's what the feature is called, and within an instant, the new schema change is in place. And obviously, this is for the nullable columns. If you're adding at end of the table, it worked beautiful. Thank you for that, Debanjan. Now, in some cases, the fast DDL may not be applicable. In that case, you either go with a traditional approach and have your own custom scripts written out. But we tried the DMS feature, the data migration. Generally, you use that to transfer data from one database to other one. In this case, we would copy from one table to a different table. And that way, we didn't have to write our own custom small batch process kind of thing. So DMS has its own internal batching, and it keeps bringing in the new data. It maintains that. If the process breaks, it just picks up from there. It was quite useful. And once the DMS is finished, we swap the tables, and now we have a new schema. Again, it really worked really well. Pretty pleased with that. Now, this is the slide, which I really want to share a few extra thoughts on that. Along the journey, we had some performance snags. When the system is up and running, the new clients are onboarded, the volume is increasing. From 30 milliseconds of select latency, we saw that it starts creeping up. And within a couple of weeks, it went beyond 100 milliseconds. Okay, no problem. So we added a few additional read replicas, and we were back in business. It dropped to 50 milliseconds. Still not quite happy with that. So we had some discussions with the Aurora team. And initially, we had a system in place, having a smaller batch processing solution. And again, we dropped from 50 select statement per batch to 20 selects or even to 10 selects. And the performance was back in line. There was one downside which we were concerned of, because now when we're decreasing the batch size, it's increasing our transaction per second, now because we're sending more transactions. But because the database was doing less work, it was quickly getting the request, sending the data back. So the benefit of having a smaller batch far outweighed the decrease with the multiple or a higher number of transactions per second. So it was a combination of scaling out with the read replicas and also the parallelization with the smaller batches. So here's some performance numbers. Replica lag is very low. Our CPU utilization is low. Insert latency, freeable memory. These are some of the main ones. Very healthy. Quite happy with that. So what does this buy us? What are the different benefits? Two. One is the monetary one. Switching from the earlier solution from Cassandra, we had about 10-15% in the dollar savings. But the real saving comes from the multiple uses from the same data set. Now we were able to slice and dice, do different querying, ad hoc querying, much, much easily as compared to Cassandra. And that's where the real savings were. Also, as far as the maintenance is concerned, initially we spent a little bit extra time when the system was kind of getting stabilized. And later on, we literally spent no time except for some patches to be applied or maybe some updates to be done. And on average, I don't think we have spent more than 10 minutes from end to end. So overall, this system is working pretty well for us. Now, I'll hand it over to Brandon. Like, what are some key takeaways?
All right. So just to summarize, so for high-scale streaming data system in this case, parallelization at every level of the system was key. So Kafka for scalable message queuing, Storm for distributed message processing, and then Aurora to be able to scale out with the read replicas. And really the key takeaway here is that Aurora let us easily create new managed read replicas in a way that was low maintenance and offered the level of scalability that we were looking for. And then as a corollary to that, in the application level, we realized we needed to do a couple things to really take advantage of that parallelization at the data storage layer, which is namely to create a database connection pool to each one of the read replicas from the application, and then chunk down the work to the right level that gave us the performance and resource utilization that we were looking for. In our case, we needed to manually do the cross-region data transfer. And again, that was so that we can have multiple read replicas in each region and only take the cross-region data hit once. In terms of flexibility for changing the schema so that we can iterate on what the data looks like and what kind of use cases we can support, those two features, DMS and fast DDL, really let us execute those changes much more easily. And bottom line across all of this, Aurora gave us the performance and the scalability that we were looking for with much, much lower operational overhead and with more flexibility. And that really let us spend more time developing product features and improving ultimately the product and the customer experience. So that's our story.
Thank you so much for listening to us very patiently. There's some few additional sessions on Aurora. Okay, which you can attend. I think we have about 5 minutes for Q&A, the bunch. Yeah.
Yes, we have a few minutes for Q&A, but we'll also be outside hanging around. Dave is going to be there, so you can take some questions. I think people are already starting to leave. All right.
Great.
Thank you.
Thanks.
Thank you.
So we need to use time on